And the essence of the Z-transform, I actually think it's helpful to first talk about the discrete time Fourier transform. The discrete time Fourier transform converts discrete signals in the time domain to the frequency domain. That is, it represents a signal in terms of its frequency content. And you can see that it's pretty similar to the Z-transform. In both cases, we're multiplying the time signal by some other signal and summing the result. So I think that if we can understand what the DTFT is doing, we can better understand what the Z-transform is doing. And to show you what I mean, let's walk through the discrete time Fourier transform with this MATLAB app that I created. This is a discrete time signal, x of n. And we can tell just by looking at the data that the signal is probably made up of a single frequency, at least one dominating frequency. So we might ask ourselves, how can we determine what this frequency is if this sampled data is all we have access to? And one way to do this is to compare the data with another signal of a known frequency and see if the two are correlated. If we find the right frequency, then we should reasonably expect the two signals to be highly correlated, whereas other frequencies will be less correlated. And mathematically, here's how we can approach this. To get a sense of correlation, we can multiply the data signal by the probing signal and then sum the result. When the frequencies are off from each other like they are here, there's going to be times when both signals are positive or both are negative. And when you multiply these, the result is positive and they add to the total sum. But when the two signals are of opposite sign, the product is negative and it subtracts from the total. And these adding and subtracting values will tend to cancel out over many samples, and the result therefore stays low. So there's less correlation. We can see here that the sum across these 20 samples at a frequency of 0.2 radians per sample is just about 0. But watch what happens as the signals get closer in frequency. A larger portion of the two signals will start to match signs, which produces more adding values, and then the summation is going to get larger. And we can see here that at 0.41 radians per sample, the summation is about 5. And then, if we keep continuing, we get to the point where they line up perfectly, and the two signals are perfectly correlated, and the sum is the highest it can be, about 10 for 0.5 radians per sample. And then as we pass through that matching frequency, the result gets low again. So in this way, we're sweeping across all of the possible frequencies, and we're getting a graph that shows how closely our data signal correlates to all of these different probing frequencies. Now, the signal that we're analyzing is a pure frequency signal, but as you can see, we're claiming there is correlation to these other frequencies as well. And this is the result of the finite length of data. There wasn't enough data to ensure perfect cancellation of the positive and negative signals, especially when the frequencies are close. But watch as I increase the number of data points. We're giving this whole process more chances to cancel terms, and therefore the peak at the true frequency gets sharper and taller. I mean, it's already off my chart. And if I had infinite data, the results would be a perfectly sharp, infinite peak at this one frequency. So in this way, more data means more accurate understanding of the frequency makeup of a periodic signal, since there is less leakage across the frequency bands. All right, cool. So we got there. We found the frequency by multiplying the signal by a cosine wave and summing the results. However, a cosine wave on its own isn't good enough because it has a fixed phase, and the frequencies in the original signal can occur at different phases. If the phase of the data signal is different than the phase of the probing signal, then there's going to be lower correlation between the two. And we can see that as I add phase to the frequency in the original signal. The correlation with the cosine wave starts to drop as there are now some positive and some negative terms in the product. And at one point, the correlation disappears completely at the real frequency. And clearly, this isn't good because as we can see, the frequency is still there in the data. Therefore, instead of probing with a single wave, we can probe the signal with two waves that are offset from each other, a cosine and a sine wave. And to separate them from each other, we can make the sine wave an imaginary signal. Now, as we adjust the phase of the original signal, we get two responses: a real component, that is the correlation to a cosine wave, and an imaginary component, that is the correlation to a sine wave. Now, as I adjust the phase of the original signal, we can see that the correlation is trading off between the real and imaginary components. The magnitude of the total correlation is the absolute value of this complex signal, and the phase shift is the argument of the complex signal. So we're actually multiplying the discrete time signal by cosine omega n plus I sine omega n. But we can simplify this equation by recognizing that cosine omega n plus I sine omega n is just equal to e to the I omega n. And the convention is to make the exponent negative, which doesn't change the overall idea of the equation, it just swaps negative and positive frequencies. And check this out. We've arrived at the discrete time Fourier transform. And that's pretty cool, right? I mean, hopefully you can see how this equation is calculating how correlated the time domain signal is with all of the different frequencies by just multiplying it with sines and cosines and then summing the result. Analyzing signals like this is useful. However, sometimes we want to know more than just the frequency content of a signal. We also want to understand something about the system itself that generated that signal. If we could understand the system, then not only do we understand the output, given some input, but we can predict what the output would be for different inputs. And we could figure out how to manipulate the system in order to get the output that we desire. And an understanding of the system itself is where the Z-transform comes in.